So here we are. This is Math 271, Calc 2. Are you in the right place? Am I in the right place? Okay. We'll just go through the syllabus really quick. And then it's posted. I'll show you Blackboard in a second. It's posted on Blackboard. I'm Mark Ashbrook. You can call me Mark. That's fine. I'm very comfortable with that. But anything respectful is fine. Okay. Email is always the best way to get a hold of me. mark.a@asu.edu. So personal questions, or you can even ask math questions over email. That's fine. I check my email all the time. If you forget, mark.ashbrook works too. But mark.a, nice and short. Office hours are here. I'll also post those in a separate place on Blackboard. So if you ever forget my office hours, they're on the syllabus. They're on Blackboard. So that's where you can find them. 1 to 3 Mondays, 12:30 to 2:15 Tuesdays. Okay, so fine print there. What's on the course? That's what we'll be finding out. All right, the textbook is online and free to you. It's just an open textbook for anyone to see. There's the URL, so you probably put a bookmark on your computer to that because you'll be going there a lot. Homework will be written assignments and through WebWork online system. That's also free to you, and that won't get going for a few weeks. All right, there's a topics calendar. You can check that out. Note, next Monday we have no class. First test is Friday, February 2nd, and we'll be taking it during class time, but not here. I'm actually going to have a bigger window of time in a different room, and you can just show up anytime in that window to take the exam, because 50 minutes won't be enough. You should shoot for more like an hour and a half. Okay, so we'll have a window like a 2.5 to 3 hour window in the morning where you can come and just so you have enough time to take the exam, and then of course no class that day because that window will be mid-morning like now. Okay, all right, and then you can see other exams, and then note that the time of the time and day of final exam is known. Okay, so make your travel plans accordingly for start of summer break. Tuesday, May 1st, that's a typo. Tuesday, May 1st, I'll change it. This is right here at 7 p.m. Okay, so please note that in your calendar, however you keep track of those things, and make your travel plans accordingly. Please don't come to me a couple weeks away and say, oh, I have flights, can I take the final early? No, you know it today. You know it today. Tuesday, May 1st at 7 p.m. Okay, this is the breakdown of the course, grading, all the fine print. So that's just standard syllabus stuff. Any questions so far? So let me show you Blackboard. This is posted on Blackboard. If you go to Blackboard, that's going to be our home base. That's where I'm going to post homework, post grades, so it'll be our home base for the course. Oh, question, please.
So for days that you have tests, what do you do if you have classes right after this?
So we'll work something out. Yeah. So yes, I will accommodate. Yeah. So, but it'll be before too. So if you don't have class before, you can start early. Okay. Yeah. But if you have 3 classes in a row, then we'll accommodate you. Okay. So here is our home base for the course. You see here the second link over here, syllabus. And there's what I just went through with you. I'll update it with that. And if you catch mistakes, just let me know, and I'll get this updated. Homework assignments are here. So right now, this will appear after class today. So what we'll do with homework, written homework will always be due on Wednesday. So every Wednesday, we'll have some package of homework. It'll consist of several items that I'll be posting throughout the week. So you can always get started early on what's up there. And then I'll have it finalized by the Monday before the Wednesday. So you want to get started early, because that's a week worth of homework. So, and here's the key: you want to definitely get going on it over the weekend. And then my office hours are Monday, Tuesday, and we'll try to get the TA's office hours to be early in the week too. So you really work at it over the weekend, and then you have 2 days to troubleshoot with us. Get into office hours, get the help that you need. Okay, and then we'll turn in all homework on Wednesday. So you have a short assignment for this Wednesday, and that is to install GC, Graphing Calculator. I'll talk about that in a second. And then there's a one-page worksheet that's just kind of a review of today's class to get you to make sure you're ready for Wednesday's class, because we'll just pick up where we left off on Wednesday. So short assignment, 2 parts for this Wednesday. Then the following Wednesday, the 17th, will be the first kind of major homework assignment. And then we'll be always Wednesdays in lectures when assignments will be due. GC, okay, graphing calculator. Graphing calculator is not what you think of when you think of a graphing calculator. You think of a handheld graphing calculator. When we say graphing calculator, GC, we mean it's a software for your computer. This is free to you. This is normally $30 for students, but we have a hookup here, and so we get that to you for free. So this does everything a handheld graphing calculator can do, and 100 times more and 100 times better. Okay? So, and will be lots of your assignments. You will be asked to be doing things on graphing calculator. So here's how you can download it for free, and in order that we can keep providing it for free, we ask that it's 1 per machine, okay? So 1 per student. Don't share this with other people. Don't put this on several computers, but you'll see Mac instructions, Windows instructions, and then for both of those, the name and serial number is the same here at the bottom. So this is key info once you start the download process. There's the name and serial number at the bottom. Okay, so 1 per student. You're going to want it on your laptop. If you don't have a laptop, you're going to want it on your home computer. Yes, sir. Right. So I'll let you know ahead of time. Some of the tests, it might be a no calculator test. Some of them I'll tell you can only have a scientific calculator, or you can have a handheld graphing calculator. But so you won't be accessing GC on the test, but you will be using GC a lot for the homework, and I'll be using it a lot in class. Yes, please.
Is it common to get the beta version is expired?
I just got an email about that, so I will, yes, I got an email about that. So if you're having some beta version expired notice, I will let you know what's going on with that. Other questions about, yeah?
Is this the same GC that you used last spring?
Yep, same, yep. But I think there's a new version since a year ago, so go ahead and reinstall it. Make sure you have the most latest version. Other questions about GC? Yeah. So if you had, let's see, Professor Mahosky or Bonnie last semester, you're very familiar with GC, okay? Or me a year ago, then you know all about GC. It's the same GC, okay? All right. Other questions about Blackboard, the syllabus? Getting started. Anything you can think of. Again, Blackboard will be our home base. That's where everything will be. So, and then I will record all of. So since I'm doing everything through the screen, I'm doing a screen recording here on my laptop. And so at this lecture videos link, I'll have a YouTube link for class later in the day. So later on today, there'll be a link here. And it'll just give you a video of today's class. So the audio is me talking here. It's the ambient noise in the classroom. And the video is everything you see on the screen. So it's a full reproduction of class. So this is never a reason to not come to class. This is for reinforcing and going over it a second time. Because lots of times you may feel like it's a little bit difficult to really pay attention and take really good notes. So that's a great chance. So you want to make sure you're comprehending and paying attention in class. And then if you want a good set of notes, then go back and watch the video and pause it and create a much better set of notes than what you might be able to get during class. Okay, so the videos are going to be a huge resource for you, really, really important resource. Because you could walk out of here, this is a common experience, you can walk out of here and be like, yeah, I got like 85 to 90% of that. It made total sense. Okay, but with all the other things in your life, you got 3, 4 other classes, you got, roommates problems, and you've got, intramurals and all this stuff, and dance and all this stuff. All right, so then things fade away within 12, 24, 36 hours. That 90% understanding that you had when you walk out of class, maybe now down to 30 or 40% recollection, okay, or retention. That's what the video's for. You got to watch those videos and go through them again. Pause them, take good notes, so you solidify what you got in class, okay? All right. So, can we ready to start? Last chance for questions. Yes, sir.
How long does it usually take to do?
I'll have them up in the afternoon of the day of class. Yep. So I'll have them. I have another class around noon, and then in the afternoon, I'll make sure that it gets posted. So, you know, by 4 o'clock on the day of class. Yes, sir.
Does recitation begin this week?
Yes, today. If you have recitation today, go to recitation. And it is important content. It's going to be kind of review content, but something that's really important for this class, which is function notation. Function notation is something we found that students don't really have the grasp that they need. And we're going to be using it a lot in this class. And so you'll go to recitation this week and do a review sheet on that. And for some of you, unfortunately, it will be new. Okay, you've never really thought of it this way before. Okay, but it's super important. Okay, so yes, go to recitation if you have it today or Wednesday or Friday. Important stuff. Other questions? Okay, so let's get started. So in Calc 1, you investigated 2 primary problems in the subject of calculus. The first one was, you know how much of a quantity you have at every moment, and you want to know how fast that quantity is changing at every moment. And then the second primary problem of calculus is the flip side of that. You know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. Okay, so these are the 2 main problems that kind of encompass all of calculus. So that's what you did. Now, some of you may not know that that's what you were doing, but that's what you were doing, okay? Or should have been doing, okay? In Calculus 1. So Calc 2 explores both of these, but most of the course is concerned with endeavor number 2. Most of Calc 2 is about, you know how fast the quantity is changing at every moment, and you want to know how much of it you have at every moment. So what we're going to do in this first week is we're going to do a crash course in Calculus 1 of problem number 2. That's what we're going to do this week. So we're in hopefully in 3 days, we're going to get through what we spent about a month on, or even 5 weeks in Calculus 1, which was number 2. You know how fast the quantity is changing every moment. You want to know how much of it you have at every moment. Okay, so to review this, our crash course, I've made a set of principles. I made a set of principles that kind of walk us through this problem and build it from the ground up. So principle number 0, so before we even kind of get to it, I have a principle 0, and that's this idea that variables vary. Variables vary. Super important idea. All right, so when you see this, 2x minus 7 equals 0, what do you think? What comes to mind? What's that? X equals 7 over 2. Is that what you're saying? 7 halves, right? So x has a value, and you solve for x, and you get it, 3.5, right? So could x be 4 or 10 or negative 0.5? Yes or no? Could x be another value? Anyone say yes? What would happen if x was 4? You'd get 1, right? So really, if x was 4, then we could just say that thing wouldn't be true. So like we could say x could be 4, but then that equation would not be true, right? Okay, so that's actually a better way to think about this. Rather than thinking x is this value and it's not changeable. So no, x could be other values. But of all the values x could be, there's only one that makes that equation true. That's a stronger way to think about this. Okay? So suppose x was defined as the number of hours elapsed since your plane left the ground. Okay? So there's the same x as above. Now it's the number of hours gone by since your plane left the ground. Now could x be 4? Does that feel comfortable to you? And what would that mean? Yeah, you've been in so at that moment. You've been in the plane for 4 hours, or the plane's left the ground 4 hours ago, or 10 hours ago. What about negative 0.5? Does that make sense? What was it? Someone said? Yeah, half an hour. So it's possible. So negative 0.5 could just be a half an hour before the plane took off, right? Half an hour before the plane left the ground. Okay, so we want to think about variables as taking on lots of values, and some real-world situation is occurring, and x is changing as time goes by, or as this situation is unfolding. X is taking on values. So x is 0, so the plane's taking off. X is 0.2. We're a fifth of an hour in. X is 1. We're 1 hour in. So as we're experiencing this plane ride, x is constantly changing. X is constantly varying. All right? That's how we want to think about variables. All right, so what about dx is a symbol you saw in Calc 1. That's actually a variable too. What does dx represent? What does dx represent? Okay, so it's some amount of change in the value of x. Okay, so in this case, dx would be a change in the number of hours elapsed. All right, so what's the difference between saying the difference between x equals 3.5 and dx equals 3.5? So x equals 3.5. X means the amount of time elapsed since the plane took off. So that is a moment in time. That is a moment in time, 3.5 hours since the plane took off. But what about dx equals 3.5? Is that the speed? No, it's a change in x. So what does that mean, a change in x? Starting from when? Yeah, so it could start from any x value. So this dx of 3.5 could start from, say, 1. All right, and then when would that dx be up? At 4.5, right? And so that dx then represents this amount of change in time starting from 1 and ending at 4.5. But that dx could also start at 5 hours, and then it would be from 5 to 8.5. Dx would represent a change from x from 5 to x equals 8.5. So dx is a different animal, right? It has the same unit. It's still hours, but it represents a change starting from some or any value of x, and then lasting, in this case, 3.5 hours to some final value of x. Okay? So, important concept. Dx is then a change, an amount of change in whatever our x variable is. In this case, the amount of change in time since the plane left the ground. Okay, so now hopefully this works now. Yes, good. Okay. Principle 1. Okay, so principle 1. So you know how fast the quantity is changing at every moment, and you want to know how much of it you have at every moment. So that problem, what does rate of change have to do with that statement, that problem? You know how fast the quantity is changing every moment. You want to know how much of it you have at every moment. So rate of change is what in this statement? Yeah, how fast a quantity is changing at every moment. How fast a certain quantity is changing, that's the idea of rate of change. That's the idea of rate of change. So this is a key kind of underlying principle, because it's what you would start with in this problem. It's what you would have. You would know how fast the quantity is changing every moment. Or in other words, you would know the rate of change profile for this quantity. So we're got to know about rate of change. All right, so let's do a little easy example here. So you're buying trail mix that costs $3.20 per pound. After scooping some mix into your bag, you decide you want more, because that's what we're like in America. We want more, right? And what additional cost will you pay for 1.5 more pounds of trail mix? Everybody figure it out. So any way you can, get the answer to this question on your own, okay? On your own. How much will you pay for 1.5 more pounds of trail mix? So how much more will you pay when you put 1.5 more pounds in your bag. So who got a quick calculation to do that? Yes, sir.
$4.80.
And how'd you get that?
3.2
3.2. He took 3.2 times 1.5. And you got? $4.80 is how much more you would pay for 1.5 more pounds of trail mix. Everyone agree with that? All right, let's hold on to that thought for a second. So in calculus and most of mathematics, what's a really important skill is you're taking a situation, a real-world situation, and we're modeling it with mathematics. What does it mean to model it with mathematics? What that means is we're going to assign symbols to model the situation, represent the situation. So here's a set of symbols that I have. These are variables, right? So x, y, dx, dy, and m. So what I want you to do quickly is I want you to write phrases that represent what all these 5 symbols mean in this situation. So let's do x together. What do you suppose, if we're looking at a kind of conventional way of assigning? All right, so he said the number of pounds. Agree with that? We'd be a little more specific than that. So yeah, that's right. Yeah.
The amount of trail mix in
Okay, yeah. So I just threw in total in there. The total in your bag, right? So it's like the total amount of trail mix in your bag is X. So I want you to and you can collaborate with the person next to you. See if you can, about 1 minute, finish these other 4. You're writing out phrases that represent these symbols. Go. Oh, and then the other thing is, in addition to the phrase, then you're gonna determine, do you know the current value of these for this situation or not? So given X, given Y, for each one of those, ask the question, do you know its current value with the situation that I've given you? Okay? Commence. Okay. So, see if this is what you came up with. Y would be the cost of X pounds. So the cost of the trail mix in your bag in dollars. DX is change in the number of pounds, right? Change in the number of pounds. DY then is the change in cost. And I'm using M to mean what? That's kind of a conventional use. Yeah, that's the price per pound, that's our rate of change. In this case, it's a constant rate of change, right? It doesn't matter how many pounds are in your bag. It's always $3.20 per pound. Okay, is X known in this situation, given this setup for this scenario? Is X known or unknown? Unknown. We don't know the total number of pounds, right? I just said you put some in and then you put some more in. We don't know that initial amount, so we don't know what X is at. What about Y? Nope. Do we know DX? What is DX? 1.5, right? So this is the idea. If you have a certain amount in there, you put this much more in, that's the idea of a change in X, right? DX would be the 1.5. All right, DY? That was that number we calculated, right? 480. And of course, we know M, right? X and Y currently unknown. Okay, so I want to write an expression. Sorry, we're in a bad place there. So write an expression using 2 or more of these symbols that represents this problem up here. So we had a little calculation that we did. So I want to apply these letters now, these variables, to that, and come up with an expression or an equation that represents that using either x, y, dx, dy, and or m. So what would it be? First of all, what did it solve for? What were we asked to find of these 5? What were we asked to find of these 5? dy. It was asking for how much more it would cost. That's our dy. And how did we find dy? He wants m dx. Agree? Yep, m dx. And so we could say for this particular scenario, we could be a little more specific and say that dy equals what? 3.2 dx. So what does $3.2 per pound mean? What does $3.2 per pound mean? What's the meaning of that value? For every pound that you have, you're going to pay $3.2. Agree with that? Okay, that's absolutely true statement, but that's a very narrow meaning of the 3.2. Okay, so this next part is maybe the most important part of today's lecture. Okay, that is absolutely true. That every pound that you have costs $3.20. $3.20. Okay, every pound that you have will cost you $3.20. But a much broader meaning would be that really, what this little equation here, dy equals 3.2 dx, gives us a much broader meaning of that 3.2. Does it tell us anything more than how much 1 pound is? Does it tell us how much 2 pound is? How much is 2 pounds? 640. Does it tell us how much a half a pound is? $1.60, right? Does it tell us how much 10 pounds would cost? Really, it tells us. Here's the key. This is today's most important thing. Given any change in pounds, the $3.20 tells you how much the change in cost would be. That's what that equation says, and that equation is how explains that $3.20 per pound, right? dx could be anything. It's a variable. It could be a half a pound. It could be 2 pounds. It could be 8 pounds. It could be 20 pounds. And given a change in the number of pounds, 3.2 will always tell us what the change in the cost will be. Do you see how that's much more broad and inclusive than just 1 pound costs $3.20? We know how much any change in pounds, what change in cost we'll get. All right? So in that equation, so this equation is how we frame the meaning of that constant rate of change, $3.20. Okay? So again, one more time. Given any change in the number of pounds, the change in the cost will be $3.20 times that change in number of pounds. That's the meaning of a constant rate of change. Okay? Make sure you review that in the video. Get it in your notes. Most important thing of the day. Okay, going on. We remove 0.4 pounds from the bag and return it to the bin when no one's looking, right? When no one's looking. What is dx now? So it has the same meaning. What's its value? Negative 0.4. How would we find dy? Right, dy is always m dx, or 3.2 in this case, dx. And we said that we know what your change in cost will be for any change in number of pounds. So it'll be 3.2 times negative 0.4, which is, 8, what is it? $1.28? Is that right? Really? Did I get it? Yeah, I think so. Okay. So what does that mean? That means if you put that much back in the bin, your cost is going to go down that much, right? Your change in cost is negative, meaning your cost will go down. M is still the same than 3.2. So that's an example of, here's something else that 3.2 dollars per pound tells us. It tells us that if we decrease the number of pounds by negative 0.4, our cost will go down $1.28. Questions on that? All right, new example. Soldier lowers an American flag from the top of the pole at 0.75 meters per second. So here's the question we want to explore here. How much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? So if you're given this situation, what should you do first? What should you do first? Model the situation with letters, with variables, parameters, okay? So again, let's define what x is, what y is, dx, dy, and m, and I'm giving you y here. I'm going to say that y is defined as the height of the flag in meters. So y is I want the height of the flag above the ground, okay? So you do the others. So write phrases for x, dx, dy, and m. And then determine if they're known or not in this situation, right? Same thing as before. So write the phrases, and for each one, determine if it's known or not in this scenario. Take 2 minutes max. 2 minutes. Go. You can collaborate, but you definitely at least want to check when you're done. Okay, what is x? The rate? The rate of time. So is it a rate? Is x a rate? Okay, so it's definitely a time variable, but time, if you said time in seconds, that's definitely not specific enough. We could define 10 or more different time variables that are all different in the situation. So we know exactly what amount of time we're talking about. And so that means a reference point, right? So time since he started lowering the flag. All right, so time since the soldier started lowering the flag. You need that reference point of what is time 0. If you don't have that reference point of time 0, it's really not clear exactly what time quantity you're talking about. Okay, y we already said, height of the flag. So dx would be then any change in number of seconds, right? And we said that could start from any time x, right? It could start from any time x, and it represents a change in time, an interval of time. You can think of it that way, a duration of time. All right, dy is a change in the height, the flag in meters. Okay, and what is m? Again, we have a constant rate of change here. It's the constant rate of change. And what is the constant rate of change? 0.75 meters per second? Okay, so height defines that positive is which way? Up. Positive, or height increase is going up. And if it's going down, then that rate of change is going to be negative. So if you picked up on that, good for you. That's important. That rate of change is negative because we have a decreasing height as time goes by. Do we know what x is in the situation? Do we know the value of x? Yeah, exactly. So yes, we do know. We do know that our starting x is 0.6, and our final x is 2.4. So really, x takes on all those values. In this situation, x is taking on all the values starting at 0.6 seconds up to 2.4 seconds. Variables vary, right? So yes, so it's taking on all the values starting at 0.6 to 2.4. Do we know the height of the flag? We don't know because we don't know what? The starting height. All right, so y is truly unknown. Okay, what is dx in this situation? Good, 1.8, right? So dx, you could write as x final minus x initial, which are just two different values of x, our number of seconds. So it would be 2.4 minus 0.6, or 1.8 seconds. If you came up with 1.8, good job. That's the duration of time. So then what is dy? What did we say? So dy would be mdx, right? Remember, so this negative 0.75, does it tell us just that the flag goes down 0.75 meters every second? Is that what it tells us? That's a very narrow meaning, right? So it tells us what? In any change of seconds, how much the flag will go down, including 1.8. How much does the flag go down every 1.8 seconds? Well, we're going to take our negative 0.75 times 1.8, and you get, who did it? Nice and loud? 1.35 meters. right? So given any change in time, that negative 0.75 meters per second, that constant rate of change, tells us the change in height for that change in time. Not just for 1 second. Any change in time, right? Including, in this case, 1.8 seconds. Gotta move. All right, so now we want to know, let's say, how much does the height change from 0.6 seconds to x seconds? So now we're going to let that final time be variable. And I want to know how much does the height change from 0.6 seconds to x seconds. So we're going to use dy equals m dx to do that. What is m? Negative 0.75. What is our dx now? Some of you are saying it. X minus 0.6. X is allowed to change now. So starting at 0.6 seconds, x is going to change. Now x is still the number of seconds since 0 seconds since the flag left the top of the pole. It's not the number of seconds starting from 0.6. It's still the number of seconds starting from when the flag started to be lowered. All right, so we want the change in height. We got the constant rate. We got the change in the number of seconds. And so this question is equivalent to asking, really, what's the net accumulation function? Net accumulation function for the flag's height beginning at 0.6 seconds. In other words, how much height has accumulated since 0.6 seconds? Or deaccumulated, right? So it's decreasing, but accumulation can be increasing or decreasing. So this question is something called a net accumulation function. Okay? And so our dy, this is going to be our notation for a net accumulation function for a sum. This is the quantity h, or height. So it's the accumulation of quantity h, and that's our dy. How much has the height changed since 0.6 seconds? And we came up with that. You guys said that the m was negative 0.75, and dx would be x minus 0.6. So this is a net accumulation function of height, particularly for the net accumulation since 0.6 seconds after the flag started being lowered. Okay, and so this is what we call function notation. You're going to be practicing this stuff in recitation this week. Super important what function notation means. It means the value of the dependent variable of this function. So there's an independent variable, and that's time since the flag started being lowered. That's x. And there's a dependent variable. And in this case, that dependent variable is the accumulation, the net accumulation of height since 0.6 seconds went by. All right, so that's principle number 2. So principle number 1 is just the idea of rate of change and what it means. We said that was the most important thing we covered today. Remember that? Principle number 2 then is a net accumulation function, like the one we just came up with. So same scenario. First we want to label, so I want to have a rate of change function on the left, and I want to have the net accumulation function on the right. So first of all, what would my units be? So we're going to do it as the rate of change function and the net accumulation function. What would my x-axis units be? So my horizontal axis units be on these graphs. That would be my x, right? So that would be my number of seconds since the flag started being lowered. What would be the units on the left graph of the vertical axis? It's the rate of change. Meters per second. That's the rate of change of height. And then for the net accumulation, meters. Okay? So what would the rate of change function look like if we were to look at, for any number of seconds, this graph is going to tell us what the rate of change is at that number of seconds. What would it look like? Horizontal line at negative 0.75. That's the rate of change function. Now, forgetting about the formula that we came up with just based on the situation. So don't try to graph the formula, but think about what will this net accumulation function look like? At 0.6 seconds, what's the net accumulation of height? Since 0.6 seconds? 0. And then what happens to the accumulation of height? Goes down, right? So imagine it's going to start at 0.6 seconds, it's going to be 0, and it's going to head down from there, right? Does that make sense? So that is our net accumulation function, the one that we wrote, negative 0.75 times x minus 0.6. Does that graph make sense? If not, mull it over, ask one of us. So like I said, your homework for Wednesday, get GC on your computer, and then do the one-page review of today's lecture so that you're ready for Wednesday's lecture.